So what's considered small in that case? We need a method to decide if the p-value of 0.0494 is considered unlikely enough. Because it is not big, it's not a tremendous probability, but it's also not as small as 0.62 up or 0.0062, which what we had before. So what we do is we compare 0.0494 to a level of significance, and we call that level of significance symbolized with alpha. It's a percentage that's provided in a word problem. In the wording of the problem, you're going to see alpha set to either 1% or 5%. We're going to compare our p-value to alpha, and based on that comparison, that will help us make our decision. If the probability of the sample statistic happening, which is the p-value, is less than alpha, then it is considered to be a small probability, a highly improbable event. So if p is smaller than alpha, the p-value is smaller than alpha, then it's considered unlikely, and as the jury, we can say that the teaching method would be more effective in that case. So in our role as jury, we're going to compare the p-value to alpha to make the decision. So like I said, alpha is going to either be set at 1% or 5%. So let's suppose alpha is set to 1% in this problem, and our p-value is 0.0494. 1% is 0.01, and if we compare alpha to the p-value, we see that alpha is not, rather we see that alpha is smaller than the p-value. The p-value is too big in this case. So what you would say is, well, the p-value is not small enough. 0.0494 is not less than 0.01, so the sample data is not strong. The assumption about the population parameter is true. So we're going to conclude that the new teaching method is no more effective than the old teaching method. The population parameter stated that the old existing teaching method gave us a population mean of 72.4. What exactly was that? 72.4, and when we come to the conclusion that the p-value is too big, then we say that the new teaching method it will produce results no better than the old teaching method. However, if we have an alpha of 5% in this problem and we compare our p-value to 5%, or 0.05, we have a p-value that's smaller than alpha. And if that's the case, then the p-value is small enough. 0.0494 is less than 0.05, and therefore the sample data is strong. The assumption about the population parameter is not true, in which case we're going to conclude that the new teaching method is significantly better than the old teaching method. A small p-value indicates a highly improbable event. Smaller p-values indicate stronger evidence that the assumption about the population is incorrect. So, if we're trying to prove something in a hypothesis test, our goal is to arrive at a small p-value. So if we look at these two scenarios, let's suppose an x bar of A gives a p-value that is represented by this piece of area, and an x bar of B gives a p-value that's represented by this piece of area. The p-value on the left for the sample statistic x bar equals A will give stronger evidence that the population assumption is incorrect. The area is smaller, and so the probability is smaller. When you have a small area in this tail, it means that x bar is far enough away from the center of the distribution to indicate a highly unlikely event. Highly unlikely event indicates that the new method or the new product or the new drug is more effective than the existing population parameter. To interpret p-values, we say that any p-value that's less than 0.01, which is 1%, is called statistically very significant. If the p-value is between 1%, 0.01, and 0.05, we say the statistical result is just significant. Anything greater than 5% is not going to be significant. Between 5 and 10, we say marginally or not significant, and greater than 10, we say not significant. So a p-value is, as I said before, if we take the area up towards positive infinity, if we're looking at the right tail, or if we're looking at the left tail, we take the area from negative infinity up to a particular point in the left tail. The p-value is that area that extends either towards negative infinity or towards positive infinity. And what we're going to do is look at p-values and see if they're small enough to reject what's being stated about the population. So this brings us to the rare event rule for inferential statistics. If, under a given assumption, the probability of a particular observed event is exceptionally small, we conclude that the assumption is probably not true. So this should make sense to you if we look at our Gestamax example. We're going to initially assume that Gestamax isn't effective and that it produces a mean pregnancy length not much different than the current population mean, 266 days. This is the same concept that's used in testing of products. We make the assumption that the product or the new product is no better than the old product or does little to nothing at all. So we make the assumption that Gestamax does nothing to a pregnancy length. We're going to say it produces pregnancy lengths of 266. That's how we start a hypothesis test, making the assumption that Gestamax is no more effective. Okay, but when we looked at the probability of getting a sample mean of women together and getting their sample mean, getting 400 women together and finding that their sample mean was 268 days or more, the chance of that happening, 0.0062, is very, very slim. So, since the chance of getting that kind of result is too small to reasonably occur by chance alone, we conclude our initial assumption was probably not true. Our initial assumption stated that Gestamax doesn't increase pregnancy length, but because the probability is so small, it's too unlikely to happen by chance alone, we have to attribute the change in pregnancy length to the vitamin. So in other words, it's not true to assume Gestamax produces pregnancy lengths the same as the general population, and therefore Gestamax is effective.